everyone, my name is Dominique Gooden. This summer, I worked in the laboratory of Paula Hammond under the mentorship of Andrew Pickering, and today I will be talking about layer by layer nanoparticles I designed for the delivery of nucleic acid to glioblastoma. Now to start, glioblastoma is a very aggressive brain cancer. We often don't see as well as treatment responses that we want to see to surgery, radiation, and chemotherapy. And with surgery in particular, what happens is even with a tumor resection, which means taking out the tumor, often what you see is that there's a lot of lingering tumor cells in the area, causing repopulation and just a bunch of aggressive characteristics we see with the glioblastoma. And unfortunately, these are characteristics that also lead to low long-term survival rates around 5%. Now, in glioblastoma at a molecular level, it's been shown that there's an enzyme in this tumor called integrin kinase, and that happens to be overregulated in glioblastoma. And that's just one factor that leads to this aggressive glioblastoma cell behavior that we see. And siRNA, a therapeutic agent, has been shown by the literature to actually reduce this expression and could hopefully we could see a decrease in terms of these aggressive characteristics in a glioblastoma. So this leads into what I did. So pretty much I designed a layer by layer nanoparticle. The way this works is that you have a liposome core that you pretty much mix a different combination of lipids together and you rotovat them, and then you use sonication to layer individual polymer levels onto it. So these were some of the polymers we used on our nanoparticle. And I know I said siRNA earlier. One thing I would like to mention is that we used ILK DNA, otherwise known as integrin kinase DNA, as a replacement for siRNA, just because this is a particle in its optimal stage. And siRNA happens to be many, many dollars, whereas ILK DNA is often cheaper. So we opted to use ILK DNA for the purposes of this project. And what we did is we pretty much layered on the particles with the sonication, and we did this over the course of a couple weeks. So we went from a bare liposome to a layer by layer nanoparticle that has all these different polymers on. And the way that these polymers are held on is that you electrostatically absorb each layer onto each other. So with the bare liposome, that's negatively charged. And then we add a layer of PLR, which happens to be positively charged. So those opposite charges cause those surfaces to absorb to each other. And then with the ILK DNA, it's negative. So positive and negative opposite charges absorb, and so on and so forth for the rest of the layers. So what we were able to prove with this was that we have a relatively stable nanoparticle size growth, as well as charge inversion. So what we see on the left is that we don't see any abnormal sizes where it just shoots up or shoots down. We see a stable step-by-step increase. And then for the charge inversion, as I was saying earlier, when you have opposite charges, they attract the layers. So when you have a negatively charged liposome core, it will make sense that if there's not any polymers on, that's negative overall. But then when you add that layer of PLR on for layer 1, it becomes positive overall. And then the layer of ILK DNA becomes negative overall. So those are characteristics synonymous with a particle we want to see. And then next, we were interested in how much ILK DNA was actually on the particles for the amount that we used. And to do that, we did a DNA picogreen assay, where we also used, when we were doing this assay, we used 2 megs per mil of heparin to pretty much bind the PLR layers on it. So that way we could quantify the amount of DNA that's on that surface better. And what happens at a more finite level is that you see the reagent from the assay reacting with the DNA that's on the particle, and that emits fluorescence in the machine that it's spread on, and then it leads to these values that we see over here. So what this represents is that layer 2 represents the initial layering of DNA on. And for that layering, as well as the layering of the PLR and the PLE PEG, that the ILK DNA remain pretty constant and stable on our particles, which is what we want to see. And then what we also were able to achieve was a 38% DNA encapsulation efficiency, which represents the amount of DNA that's on our particles for the amount that we use, and its ability to load drugs per meg of nanoparticle. So our main takeaways was that we can incorporate the integrin kinase DNA into these nanoparticles that we were able to create, which the final size was around 200 nanometers, and we were able to maintain the small size and colloidal stability that we wanted. And then we were also able to attain a high DNA loading and encapsulation efficiency, which 38% is good, very good for the numbers and for the purposes of what we wanted to see. And we didn't see any significant DNA loss from the particles for each DNA, or not for each DNA layering, for each polymer layering. And then finally, we were able to see that heparin complexation with the PLR that's required to obtain reliable DNA quantification, because originally when we did not use heparin, we were not getting the values that we wanted to see. So heparin helped to further expose the DNA so we could actually quantify it in its true form. So we have tools to design better therapeutics, but they must be further optimized and defined. And this leads to my steps for future direction. So we would want to do the same exact process with the siRNA. And that is actually what some of these graphs show over here, where so far when we've layered it at different weight equivalents, so far 1x molecular weight equivalent seems to be best. We see the same average size where you don't see any crazy abnormal values for the size in nanometers. And then the charges, since siRNA is negatively charged, we would see or expect to see the, you would expect to see negative values for that too. So since 1x seems to be the best weight equivalent, and that was the weight equivalent we used to layer the DNA onto our original nanoparticles, it shows that there is a bridge of translation for what we see. And then finally, we would want to perform an in vitro inspection assay and test the nanoparticles onto the glioblastoma cell lines to measure how much integrin kinase is knocked down. And finally, these are my acknowledgements, and thank you for listening.